Hi, welcome Debashi. So in this mock interview round, we are evaluating the concepts of overfitting and gradient descent for a beginner machine learning engineer. And we are going to get started with the questions now. So the first question is,
what is overfitting in machine learning, and how can gradient descent settings indirectly affect it?
So overfitting in machine learning is when the model is uh, trained in the training data, and when it uh, faced with unseen data, it cannot give the proper predictions as was expected. It's more uh, used to the training data itself rather than recognizing patterns in the unseen data. So, and gradient descent settings can indirectly affect it when certain data sets where the saturation occurs, where uh, some of the values in the data set are too highly positive or negative. So that way, the when it comes to adjusting the weights, the uh, proper adjusting the weight doesn't happen properly, and uh, the uh, the weights and the biases don't the weights and the weights and the biases don't fit the uh, are not calculated properly to uh, give the proper prediction as was expected.
okay, let's get to the next one.
How would you tell if gradient descent is causing poor generalization, and what simple changes would you try first?
So gradient descent is causing poor generalization is uh, is causing poor generalization the uh, the when the calculation of the weights by adjusting with its error are not as accurate as we would like it to be due to saturation. So what we would do is rather use instead of using sigmoid activation, we would do a ReLU algorithm to get the proper training data, to get the proper calculation of the weights and then adjust it accordingly.
Okay, let's get to the next one.
If training loss falls but validation loss rises, how would you decide whether overfitting or a poor learning rate is the main issue?
So, if the training, I would give the model some unseen data. So, and then if I would look at the performance if it's able to give the accurate answer or not. If we see that on training data the error is marginal and on during the validation the training the loss is much higher, then it would definitely be an overfitting issue. Otherwise, it would be a poor learning if the training loss falls as well.
Okay, okay, let's get to the next one.
What simple experiment would you run to separate overfitting from a bad learning rate, and what result patterns would you expect?
The only experiment I can think of currently is To run the separate overfitting from a bad learning rate is I would split the training data into two sets. One is training data and one is the validation data. Uh, if I see the model is able to predict accurate results for the training data itself and not for the validation one, then I would realize that this is a overfitting issue.
Okay, sure. Let's get to the next one.
After fixing the learning rate, what regularization methods would you try next to reduce overfitting? And how would each affect training and validation loss?
Uh, uh, as I said that to reduce overfitting, I would use the ReLU algorithm instead of the sigmoid activation. That way, we can minimize saturation and for highly positive and negative values. So that way, we could minimize the training and validation loss.
Okay, let's get to the
How would you use learning curves to confirm overfitting after gradient descent is tuned? And what patterns would guide your next fix?
Uh, to check to see the learning curves and to confirm overfitting, I would plot uh, the into a graph, and if usually for sigmoid activation, it creates an S uh, line on the graph, and if the slants on the positives and the negatives part is too flat, then I would realize that overfitting is likely due to saturation. So I would try to create a more I would try a different algorithm to try that, but I will read up on it a little.
okay, sure. Let's get to the next one.
How would batch size influence gradient descent behavior and overfitting risk? And what trade-offs would you watch when choosing it?
I'm not sure about batch size, so I will read up on that. I haven't. I had used a very small training data to uh, train my model, which I also split into training and validation models. So batch size I will have to read up on.
Okay, great. Let's get to the next one.
How would you compare early stopping with L2 regularization for controlling overfitting? And what training loss and validation loss patterns would justify choosing one first?
How would you compare this? I would have to read up on this. I'm not so sure about this one. So it's a bit complicated than the one I've done.
No problem. Let's get to the next one.
How would you tune momentum or Adams settings if loss oscillates? And how would you check whether the fix improves stability without increasing overfitting?
Yeah, this also I would have to read up on it. I'm not sure about tune momentum and Adam settings.
Okay, let's get to the next one.
How would you use cross-validation to confirm overfitting after gradient descent is stable? And what results would change your next model or regularization choice?
Uh, I would feed the model some unseen data to see if the validation and the new unseen data are similar. Are the model is predicting similar results or not? And what does this would change your next model? And the model I would choose in order to would be ReLU or Garilla one.
Okay,
Yeah.
let's get to the next one.
How would you explain bias variance trade-off here and use it to choose between a simpler model, more data, or stronger regularization?
Uh, I would check for um, sorry, the for bias variance trade-off here. I will check for collinearity between the features, and if the error margin is on the lower side, then I would stick with the model. I would use more data in order to uh, see if the issue is with the training data or the I would see the for the unseen data. I will fit the model. I would check if the model is able to predict the correct predictions or not. But first, I will start with the collinearity between the features. If it's not an issue, then I would check the data set if I can have more data or not. And if model is still and if the data set is correct and the model is still not able to predict the proper prediction, then I would go for a different regularization technique.
Okay, sure. Let's get to the next one.
How would you decide between early stopping and adding more data when validation loss worsens, and what evidence from training runs would support your choice?
Uh, Adding more data when validation loss worsens. If I see that validation loss is worsening, uh, then I would uh, then that's definitely an issue of overfitting, and then I would go for a different uh, regularization technique. I would choose a different algorithm for the model to be able to predict, and then I would run the same data set and see if that issue is recurring or not.
Okay, let's get to the next one.
How would you confirm whether stronger regularization is helping generalization versus simply slowing gradient descent, and which metrics or curve patterns would you compare?
For the metric, for the curve pattern, I would plot it into a graph, and if I see that the pattern is taking more of an S shape, so I will realize that due to stronger saturation within the data set, uh, the uh, the weights are are not probably getting adjusted rightly. So that could be a chance of overfitting there. And for simply, and the metric I would use is the I will check on the metric. So, but yeah, the curve pattern I will see for the S1 to see if this gradient descent is slowing down or not based on the S-shaped curve.
Get to the next one.
How would you diagnose vanishing or exploding gradients during training, and what simple fixes would you try before changing the model architecture?
To check if I have vanishing gradients, that means it's definitely a case of saturation within the data set, so, which means we have highly positive or negative, uh, either positive and negative values within the data set where the weights are not getting adjusted properly. So the simple fix would that be we could uh, add more data into the data set to model to check the patterns first, and what we can do is we can adding more data and would be the better fix here.
Okay, sure. Let's get to the next one.
How would you choose a learning rate schedule to improve convergence while reducing overfitting, and what training validation patterns would show it is working?
Uh, I'm not sure about a learning rate schedule. I would have to read up on it.
Okay, let's get to the next one.
If training loss keeps falling but validation loss rises, how would you decide whether to simplify the model or apply dropout first?
Uh, if training loss keeps falling and the validation loss is rising, uh, then what I would do is I would decrease the data in the uh, I would uh, increase the data in the training model first for the I will take the data from the validation uh, side to the training side for the model to be better equipped with the patterns within the training data to be able to adjust the weights properly. And then I would also increase the number of iterations uh, al- uh, of the algorithms for it to for the propagation to occur and the number of epochs actually. So the model can be better trained in the patterns of the and gets better adjust of the weight.
Okay, let's get to one last question.
How would you distinguish underfitting from overfitting using training and validation loss curves? And what first gradient descent related adjustment would you make in each case?
Uh, uh, to see if we are getting the best way to check for underfitting and overfitting issues is by feeding the model some unseen data. If the if we see that the model is performing well under the trained data, then it's definitely an overfitting issue. If the model is uh, not giving proper output for the unseen data and the training data as well, then it's definitely an underfitting issue. So that means we would have to change the algorithm. Uh, and if it is an overfitting issue where it is only underperforming in the unseen data, then it's an overfitting issue, and we would have to make an adjustment on how the weight is calculated.
Okay, sure. Great.